Hi, welcome to the video abstract of the paper on irrationals with Lagrange value exactly 3. I'm Zhe. This is a joint work with Harold Erazoa and Professor Carlos Gustavo Moreira. First, let me introduce the background of Lagrange and Markov spectrum. The Lagrange spectrum is a closed subset of real lines that appears naturally in the study of Diophantine approximation. The Lagrange value of irrational x, kx, is defined as the supreme of constancy such that this inequality has infinitely many rational solutions. And the Lagrange spectrum is a set of all finite Lagrange values we denote as L. And through continued fraction, we can get an explicit formula of Lagrange value kx, which is the lim sup of these two sums. And in the following, let n denote the set of non-negative integers and n star denote the set of positive integers. Perron gave a dynamical characterization of Lagrange and Markov spectrum. And we consider the symbolic dynamical system where the capital sigma is a symbolic space, which can also be considered as the space of bi-infinite sequences, and the small sigma is the left shift. And we can define a function lambda from sigma to r as the sum of these two continued fractions. As a consequence, we have an equivalent characterization of Lagrange spectrum, which is a set of all finite values of Lx, where Lx is defined as the lim sup of lambda sigma nx. On the other hand, the Markov spectrum is defined as a set of finite values of mx, where mx is the supreme of lambda sigma nx. The initial part of Lagrange and Markov spectrum was first characterized by Markov, which says that the initial parts of Lagrange and Markov spectrum coincide and is a discrete sequence accumulating at 3. As a consequence, the Lagrange spectrum before 3 is countable. And moreover, it is known from the proof of Markov theorem that the preimage by K of the Lagrange spectrum before 3 is also countable. On the other hand, it is known since the 1950s that the set of Lagrange spectrum before 3 plus epsilon for any epsilon bigger than 0 is uncountable. For c bigger than 0, let xc denotes the set of irrationals that this inequality has only finitely many rational solutions. And we have the following containment relationship. As a consequence, the set xc is uncountable for c bigger than 3 and is countable for c smaller than 3. In the number theory book by Bocello, Martinez, and several other authors, including the third author of this paper, in chapter 8, the following result was claimed without proof. It says that the set X3 is uncountable. But after checking references about the Markov and Lagrange spectrum, it seems that this problem has not been considered. This would be a natural question even in the 19th century. Our main result is following. For n non-negative integers or n infinite, let the set x3n denote the set of irrationals with Lagrange value exactly 3 and such that this inequality has exactly n rational solutions. And we prove that x3n is uncountable for every n non-negative integer or infinite. Our proof of the theorem is inspired by Bombili's proof of Markov's theorem, where the set M inverse 3 was characterized through the renormalization method. Let pi be the projection of the symbolic space to the positive part, and we define the set Y3n be the irrationals such that they are in X3n and they are also the projection of some elements in M inverse 3. We actually prove that the set y3n is uncountable for every n non-negative integer or n infinite. And this is the main references. Thank you for attention.